Today we're looking at section 4.1, which deals with probability. Now this is sort of a sidestep from what we've been working with, but we're going to come back and use what we learn in section 4.1 through 4.3 to help us with some probability distributions later. So just keep that in mind. We're going to be using this. So today what we're going to consider are what are sample spaces and how do we find the probability of an event using classical, empirical, or subjective probability. Now probability is really just a very simple definition. It's the chance of an event occurring. And as it says here on the slide, we can use it to quantify what the odds are that a certain a specific event will occur. Some examples of how probability is used every day would be weather forecasting. For example, the 75% chance of snow, or even for things like setting insurance rates. So we all use probability every day. So we have four definitions that I want you to be aware of. The first one being the probability experiment. And all that is a process, a chance process that leads to well-defined outcomes well-defined results, which are called outcomes. So I'm going to be using that word outcome throughout the rest of this section. And an outcome is just the result of a single trial of some probability experiment. The sample space is the set of all possible outcomes of that probability experiment, whereas an event is just a subset of that. So it's just a smaller grouping of all of those outcomes. Now, in our sample spaces, we need to be able to determine what are the set of all possible outcomes. So with the first problem here, this one about tossing the coin, we're thinking about, okay, this is a fair coin. It's not something special with two heads or something like that, or been shaved on one side, so one side lands more often than the others. It's a fair coin. So when you toss a fair coin or flip a coin, you expect to get one of two outcomes, heads or tails. So that's our sample space. Notice that it's within braces because this is a set of all possible outcomes. When we roll a die, now that's a single die. So we only have one, and when we roll that single die, these are our possible outcomes. We could get the numbers 1 through 6. Or if we're answering a true-false question on a test, it's either one of two outcomes. It's either true or false. Now when we're tossing two coins, notice how the outcomes are listed here. It's possible we could get a head on the first coin and a head on the second, or we could get a head on the first coin and a tail on the second. Or we could get a tail on the first coin and a head on the second. Or we could get tails on both coins. So there are four possible outcomes. This is a set of all possible outcomes in tossing two coins. If we're rolling two dice, now here we have to think, one single roll of the die produces 6 outcomes. But now we've got two dice. So what's happening here is that maybe we roll the die, and on the first roll, with the first die, we get a 1. And we roll the second die, and we get a 1. So this is one of our outcomes, 1, 1. Now, if we keep the first die 1, so that's going to stay constant, and we just change the second one. So the second one, we could get a 2, we could get a 3, we could get a 4, a 5, or 6. So those are our possible outcomes with 1 on the first die. But we could have had a 2 on the first die. And if we do that, and then just change the second die, notice these are our outcomes here. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. Or likewise, change a 3 on the first die. These are going to be our outcomes. So as I go through this process for each one of these, notice that we have a total of 36 outcomes. Now, we're going to need this with some of our problems, knowing how many outcomes are in the sample space. And this table is reproduced for you in the textbook. Sometimes when I write down the table, I'll write it like this. And the reason I do is to get away from all those parentheses and commas. I know that when I look at this, this is the set here, and this is written as a matrix. So this 1, 1 is not really 11. That means 1 on the first die, 1 on the second die. This means 1 on the first die, 2 on the second die, and so on until I get down to 6 on the first die, 6 on the second die. So we're going to have to use this list of all possible outcomes when we solve a problem that involves 2 dice. Now, looking at a standard deck of cards. Standard deck of cards. So there's no jokers or anything like that going on in that deck of cards. Well, our sample space here with a standard deck of cards, we have 52 cards total in the deck, 52. Now, we need to kind of visualize what these 52 cards look like. Well, the deck is separated into 2 colors. We have half the deck is black, and the other half of the deck is red. And we also need to think about the suits that these red and black cards are divided to. So with red cards, there are 2 suits, which are hearts and diamonds. And with the black cards, there are 2 suits, which are spades and clubs. And within each of these 4 suits, we have 13 cards. Now, when you start listing these cards, if we start with the ones that have numbers on the card itself, then it's going to be numbered 2, 3, 4, all the way up to 10. That's our numbered cards. And then we have face cards. And the face cards are Jack, Queen, King, and then a very special card, an ace, could either be counted as a high card or it could be counted as a low card. So these are the cards in the suit of spades, 13 of them. Well, clubs has the same 13 cards. Got 13 clubs, those same values. Hearts has 13 cards in the deck. And diamond, there are 13 cards in that suit. So we just need to be aware of what that looks like when we're getting ready to answer a question. Now, in this particular problem, it says find the sample space for the gender of a family if a family has 3 children, using B for boy and G for girl. Now, when I look at this, they give us the sample space there at the bottom of the page. And you might be thinking, how in the world did they get that sample space? Well, there's a process that we use. And one way to designate this is to use a tree diagram to say, okay, the first child that's born in this family could either be a boy or a girl. And the second child that's born in this family could be either a boy or a girl, regardless if the first child was a boy or if the first child was a girl. Kind of looks like our heads tail problem here, right? We've got 4 outcomes: boy, 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 girl, girl, boy, girl, girl. But I'm looking at third child. So from this last one here, we could have either a boy or girl. And from this one, a boy or girl. Because it doesn't matter what the gender of the first 2 children were. Boy or girl. So now when I get ready to list my outcomes for that, what I'm going to do is read along the branches. So like this first one here, the outcome is boy, boy, boy. I know you can't see that. The second one, the outcome would be boy, boy, girl. The third one, the outcome would be boy, girl, boy. And this is where we're getting these things down here at the bottom of the page. This is where they're coming from. And then the fourth outcome, reading along the branches there, would be boy, girl, girl. And then our next outcome, reading along the branches there, would be girl, boy, boy. So I hope this kind of clears up where these outcomes are coming from in that list of 8 possible outcomes. But if I'm given a problem in which I'm looking at the gender of the children born in a family of 3 children, this is the way I need to consider it. I've got 8 possible outcomes in my sample space. A little bit better looking graph, this one here, is also found on the slides. Now, once we determine what our sample space is, then we can go back and do some probability problems. And we're going to look at classical probability first. Classical is what most people are used to. In this one, you use the sample spaces and you say the probability of an event occurring. This is the probability that an event occurs is equal to the number of outcomes in the event divided by the number of outcomes in the sample space. And we're going to use the same rounding rules as we do with everything else. If you want to round your final answer off to 2 or 3 decimal places, is fine. But I would prefer that you stick with reduced fractions unless you're asked to round off to 2 or 3 decimal places. So let's look at a problem. Here we have with a single roll of the die, what is the probability that we roll a 3? Well, how many 3s would you get? If you roll a single die, what are your outcomes? 1, 2, 3, 4, 5, 6. So you got 6 possible outcomes. That's your denominator. How many of them are a 3? Just 1. That's my answer. If I roll 2 dice, what is the probability that the sum of the faces is 5? Well, that's probably where I'd go back and look at my 6 by 6 array. Going back to this. And I'm looking for the sum of the faces to be 5. So I add 1 and 4 together. That's 5. 2 and 3. That's 5. 3 and 2. 4 and 1. So I've got 1, 2, 3, 4 outcomes that will produce a 5 out of 36 total outcomes. So to get that answer, it's going to be 4 out of 36, which is 1/9. And you do want to reduce fractions. Draw 1 card from a standard deck of cards. What's the probability that I draw a black 10? Well, you have to remember there are 2 suits that are black, the spades and the club, and there's a 10 in each one of those. So there's 2 black 10s out of 52 cards. And then we just reduce that to 1 over 26. And in a family of 3 children, what's the probability of 2 girls? So going back to that little tree diagram we had a moment ago, the probability of 2 girls. So as I'm looking at this, I could get 2 girls here. Let's see, 2 girls here, 2 girls here. Now that has 3 girls. And it didn't say at least 2 girls. It just said probability of 2 girls. So I don't want to include that. If it had said at least 2 girls, then I would. But I'm only going to use these 3. So going back to my question, I've got 3 outcomes that have 2 girls out of 8 total outcomes in a family of 3 children. And this kind of explains it as well. These are our basic rules for probability. And with these rules, I'd like for you to notice that our answer is always going to be a fraction or decimal between 0 and 1 included. So in the second one here, where it says if an event cannot occur, if it cannot happen, then its probability is 0. So for example, in rolling that fair die, if I said, well, what's the probability that I roll a single die and I roll a 7. Well, that can't happen. So